Welcome. When one typically thinks of conventional forestry, they think of removing the stem to manufacture harvested wood products. But actually, a large proportion of the biomass of a tree consists of forest residues, which could be removed from the forest and utilized for bioenergy. So, in this paper, this is actually what we set out to do, entitled Climate Impact Potential of Utilizing Forest Residues for Bioenergy in Norway. And we consider the climate change mitigation potential of utilizing these residues to replace fossil fuel systems. So our case study consisted of several regions throughout Norway where we considered only Norway spruce-dominated stands. So it still remains to be the main forestry practice in Norway to leave most, if not all, forest residues in the forest. And as you can see by this figure, over 50% of the biomass, and thus the carbon in the biomass, is consisting of residues which could be removed for bioenergy. So in this study, what we want to look at is the extraction potential and the ability to mitigate climate change by utilizing these residues. We consider three cases. Case A, 75% above and just above ground residue removal, just consists of removing the branches, the foliage. Case B also considers this, but also additionally removing the 75% of the below ground, which consists of stumps and roots. We also consider a more extreme case of removing all the biomass entirely and utilizing these residues for energy. And we consider 5 regions, as you can see here. But what is actually feasible? There's technical and environmental limitations in practice, and this needs to be considered. So it's very likely that the 75% removal of above ground residues is more likely, and therefore we're just going to focus on the results for this case A. But first, let's look at the dynamics when we leave the residues in the forest. As you can see in this figure, when all the residues are left in the forest, the CO2 emissions from the decaying biomass in the red curve far outweigh the sequestration of the biomass, as you can see in the green curve. And the black curve is the net. So you can see that in the initial 2 to 3 decades, the forest is actually a net CO2 source. In other words, it's emitting CO2 emissions. And so what we find is from this we find that while the CO2 remains in the atmosphere, it creates a global warming effect. And when it is removed by the regrowing biomass in the global oceans and biosphere, a temporary cooling effect occurs, as you can see in figure A, right here. But overall, the cumulative energy added, which is in figure B, to the atmosphere, remains positive over the long time horizon of 500 years. But what if we extract these residues to replace fossil fuels? So this is what we consider. We consider replacing oil, natural gas, coal, and diesel oil in providing 3 types of energy service: district heating, electricity, and transportation. So here are the results, the main net results. I realize that this is a lot of cases to take in, so we're just going to focus on the cumulative or integrated global change in temperature, which is the last column of figures, as you see here on this side. So zooming into the district heating case, we can see for case A that there's various payback periods when forest residues can replace fossil fuels. So with oil, since oil is much more carbon intense than natural gas, you can have a much shorter payback period, about 5 to 10 years, depending on the region. But with natural gas, it takes much longer, 17 to 36 years. So this is significant. With electricity, it's the same story. If you can replace coal, which is, again, much more carbon intense than natural gas, you can have a much shorter payback period, 5 to 10 years, if you remove those residues to replace coal. Whereas with natural gas, it takes a little bit longer, but it's significant. When looking at transport fuel, we see that the payback period is much longer than the coal, electricity replacement, or district heating, which spans about from 50 to 90 years when we consider case A. So in all, when we consider not just case A, but case B and case C, where we're saying 75% of a below and above for case B, and also 100% of the removal, we get quite a span of ranges of payback periods. You can see it spans from 0 years, when you can replace oil for district heating or coal for electricity, or all the way up to 100 years for some extraction cases and regions. So there's quite a variety of ranges that we must consider how to utilize our residues in the most efficient manner to mitigate climate change. So here's some conclusions. Our forest residues, they do contribute to global warming when left in the forest. This is what we found. The fast emissions out from the residues and the slow initial sequestration from the Norway spruce stands regrowing, it actually creates a temporary global warming impact. And when integrated over time, this warming effect actually will last over the 500-year time horizon. We recommend, yes, we should use forest residues to make energy that can actually replace fossil fuel. And we found that we can have a rather short payback period if we can replace these carbon-intense sources of energy, such as oil or coal. Yeah, as you can see, it is very important to note that if we can replace if we can have a lot of direct replacement, a lot of direct retrofitting of district heating or coal, where we can do co-firing, for example, these are the best displacement options. Whereas the ones with longer payback period consist of natural gas electricity or replacing fossil diesel. Lastly, permanent soil carbon can be an issue. It's something that we did consider in our sensitivity analysis. I don't show results here, but our results show that actually a quicker payback period can be gained for case A than for case B. So this gives some emphasis on the case A could actually be better to not remove the below ground. And what we predict is that more permanent soil carbon will be lost if the stumps and the roots are removed. And this is quite clear, as the soil will be more greatly agitated if these below ground residues are removed. So our recommendation is to play the precautionary principle out and just focus on 75% of above ground residues. So thank you for joining this Industrial Ecology Research Spotlight series.